Okay, let's begin. So, still we are talking about regularization, and we learned about dropout in the previous lecture, which, as I told you, is very popular and very effective method. The last thing that I want to tell you about regularization is a technique which is called batch normalization. It's a paper that published in 2015, and again turned out to be a very effective method. It is a built-in function now in many packages, batch normalization. So I don't know, are you familiar with the concept of covariate shift or domain adaptation? Okay. You know, in many, it's not about neural network. It's a general concept. In many cases, you have a problem which is called covariate shift in learning. And the solution for covariate shift is domain adaptation. The problem is that you are training a model on your training set, and then you want to test it. But the distribution of your test set is different from the distribution of your training set. You know, for example, you are modeling, you are basically making a model to predict breast cancer. And you have a training set. Training set is based on the patient that you had so far, those who came for a test, and some of them had breast cancer and some of them didn't. And usually people at age 40 or so, you know, start to get concerned about their health, and they go to physician and make a test to see if they have any problem or if they don't have. Okay, so this is your training set. But you want to test it on everyone. You want to test it on someone at age 20 to see if this person has breast cancer or doesn't have. So clearly the distribution of your test set is very different from the distribution of your training set. And the model that you trained is not going to work on your test set. Okay, another example, you are making a model for like sentiment analysis, for example. You are reading comments, and you want to decide that this comment is a positive comment or is a negative comment. And you are doing this for, say, Amazon, for example. And you are training your model for books. You know, you are looking at the comments that people written for books, and you are training a model, decide if this comment is a positive comment about this book or is a negative comment. Then you want to test your model for sentiment analysis or on another product, on the camera, for example. The distribution of words in the sentence is different because, and the way that basically they convey the semantic. You know, someone has written this comment for a book that this is a book that I return to every day. It means it's a very good book. You know, I read it every day. But for camera, someone says that this is a camera that I returned the first day. It means it's a very bad camera, you know. I didn't like it. So it's a very different distribution. So this is called covariate shift, or gap between test and train distribution. And the solution for this is domain adaptation. Domain adaptation is basically a family of techniques that try to make the distribution of test sets similar to the distribution of training set. So people who published this batch normalization paper actually had a pretty wise and interesting observation about neural network. What they realized was that we have a problem similar to covariate shift in different layers of neural network. Basically, when we are learning, when we get to the hidden layer, say this is the first hidden layer, and the second hidden layer tries to learn something from the first one, okay? But in this next iteration and the iteration after and after, it's quite possible that the distribution of this, the output of this hidden layer is very different from the distribution that we learned before, because we are applying a nonlinear function to the output of this layer, and this could be quite nonlinear, and completely shift the covariate, and the second layer cannot learn properly from this one. So let's try to fix this, okay? So suppose that you have an activation function, like a logistic function, and the input to this logistic function is a very simple linear. And then you apply it could, different things could happen, based on the value of ax plus b. You might be in this regime, which is almost linear, or in one of these saturated regimes. You might be here. And if you are here, you are in trouble, because of this vanishing gradient problem, because in backpropagation, the gradient is small, and when you backpropagate, then it's going to vanish after a couple of. So you don't want this to happen. That's one thing. And the other thing is that basically you don't want to get your covariate shift a lot during the learning, So something ideal would be that you can keep covariate around the center, somewhere here. So you don't let the covariate shift a lot. You don't let the distribution change a lot. And, we have many pre-processing steps usually in neural network. Many of them are to take care of this sort of problem. We are trying to initialize weights quite carefully, choose weights close to 0. We choose weights close to 0 to be in this regime, not in the saturated regime, right? And we choose a small learning rate. We don't want the weights to be, explode. And we are using rectifier units instead of sigmoid, again, because we want to avoid, this small gradient, and we don't want to be in this regime. So, but it seems that all of these problems are a side effect of this covariate shift in different layers that we are trying to solve it by, a smart or careful initialization, or using rectified unit, and so on and so forth. So we can't afford actually to do proper adaptive, learning, domain adaptation in any layer, because it could be computationally expensive to try to match, the distribution of this with another distribution. But the idea here or intuition here is quite simple. And, this is basically the problem that I was explaining. When you apply the second hidden layer and the first hidden layer, this is the output of the first hidden layer, and you're applying the second layer on it, and the distribution of this output may change during the learning, and it causes the problem. So the idea is quite simple. Let's normalize the data after each layer. So take the mean out divided by variance. Okay, centralize the data, make the variance equal to 1 after each layer. So in this case, you are here. You're around 0, and you don't have much variance. And you do it every time. Okay, so it's not computational, it's not expensive. You can do it quite easy. In batch learning, actually, you have a batch. You can compute the mean of the batch. You can compute the variance of the batch, and you can normalize it. So basically, if the batch size is m, you can compute the mean, and you can compute the variance, and you can normalize the data. But after that, try to rescale the data. If I multiply x by a constant, that would be the variance. Suppose that you have data which is 0 mean and unit variance. I multiply this by a constant, that c, gamma here. So the variance would be gamma squared, right? And I add beta to this, then the mean will be beta, right? So rescale the data, but treat this gamma and beta as new parameters of the model. roughly speaking, you can think of this method as, okay, after each step, I'm going to normalize the data, make it zero mean, unit variate. Then maybe I'm wrong. Maybe it shouldn't be that way. Let to rescale the data to some other variance, not 1, and some other mean, not 0. But let's model decide what would be the appropriate mean and what would be the appropriate variance. So these are my parameters. So when I do backpropagation, I take derivative with respect to them, and I try to fix them. Okay? So it's a very simple idea, very effective in practice. Yes?
Sorry, I don't understand why zero mean and unit variance is bad in general. Why do we want the model to learn gamma and beta?
You are forcing the distribution of the data to be always, say, for example, if the data is Gaussian, say, for example, you are forcing this to be a spherical, right? It's not quite clear that it's always a good practice, because after each thing that, it's not a pre-process that you do it and then let the model learn. You're doing this after each hidden layer, Hidden layer learns some parameters, and then you take the output of this hidden layer and you change it. The output of this layer is a parameter, if a function of these parameters. You apply this function, but then you change the output of the function without changing the parameters. See what happens?
Right, I understand that part. I guess I just have no intuition about which mean and variance should be the best mean and variance after you go through one period.
So we don't know which one would be the best, and that's why we let the network to decide. What's happening is that the output of this function, the output of this layer, we would like to have, we don't want this to have a huge variance each time, and shift the covariate in a way that it's hard for the next layer to learn what happened here, okay? We don't want this to happen. We don't want to change the distribution here. So, and we can't afford a proper domain adaptation here because it's, computationally too expensive. So I force the output to have a certain distribution, not necessarily the appropriate distribution. Okay? I force it to have a certain distribution. I would say, okay, your mean is 0, your variance is 1. But who knows that this is the correct distribution for this? The only thing that I want to avoid is that I don't want that the variance is such that the covariates shift and, I'm suddenly somewhere else that this model cannot learn. It has nothing to do with what has been learned in the past iterations. So I will force it to be at 0 and variance 1, but I have to have some flexibility for the model to adjust it if it's very off. Yes?
What should we do on the test time? Because at that time we don't have the variance.
Yeah, good question. At test time, you replace the population of the mean of the population, the variance of the population, not the batch, the total mean. Yeah. Yes.
What is epsilon again?
What is? Oh, this epsilon is just for numerical stability. Because if you don't have it, you may get numerically in computationally, you may get to instability. It's a very small value that you add. So mathematically, it doesn't mean anything here except that computationally, you can avoid some sort of instability that may happen.
How is the old system unstable if you remove epsilon?
Sorry?
What leads to the instability if the epsilon was not there?
If epsilon is not there,
Yeah, what causes the instability if the epsilon is not there?
the causes the stability would be that if sigma is too small. Then you add some value. So in practice, it's pretty effective method. These are a couple of examples from this paper in 2015. First of all, this is a distribution after a hidden layer without batch normalization, and this is with batch normalization. Just visually, you can confirm that the distribution changes a lot when you don't apply batch normalization, and it's way more smooth if you do apply batch normalization. In terms of training time without batch normalization, that's the training curve, and with batch normalization, this is the one. It learns way faster, and intuitively it's clear why it learns faster, because this hidden layer here, when you don't have batch normalization, needs to learn a variable which varies a lot, but somehow you restrict the variation of this data here, so you help this layer to learn faster. Also, it helps that you can choose possibly larger learning rate. So they have many experiments in that paper, and they show that it's faster. I mean, it converts faster, and it helps for performance. And sometimes it's faster, even 30 times, with batch normalization. So they have many experiments here that I skip. If you want to see, look at the paper. But it is a built-in function in many packages, including cross that I'm going to show you. Yes?
Is the gamma and the beta, is it learned by the neural network?
Yes.
The inputs, like weights which we give?
Sorry?
Well, when we say that beta and gamma, is that learned by the network itself, like the weights which we
Yes.
give to the back?
Yeah, exactly. This is new parameters of the model.
So does that mean that it requires new activation units in the network, or?
No. This will be, you take the output of one activation, you normalize it. After normalization, the mean is 0 and the variance is 1. You multiply this by a constant. This constant is a parameter. And you add a constant to this, and this constant is another parameter. And you learn these two constants using backpropagation.
You can think of it as just extra layer, right? The gamma and the beta.
Yes.
Yeah.
This is actually how Keras implemented. It's another layer.
I also have another question. So what if you transform the data, and a lot of the information about the transformed data is encoded in the higher moments? Like, is batch normalization still effective, or is it people have this tested on a rather limited kind of data set?
Like, can you explain more?
So, for example, let's say that you started with a data set that has relatively simple distribution, but then you do some sigmoids or whatever, and the data set that you get out on the other side is something that has a very wild distribution with lots of higher moments and so on. In that case, the variance and mean are really not going to capture that much, right? So, yeah, in those cases, is it still effective, or?
In practice, actually, the distribution in the higher order layers would be simpler than the distribution that you have in the input. It's possible that the distribution that you have in the input is very, non-smooth, and distributions of the hidden layers are more smooth. But it's very unlikely that it's the other way around, because somehow it's like kernel methods. In kernel methods, you map the data in higher dimensional space in some Hilbert space. The structure becomes more linear there. Very roughly, it's not quite correct, but very roughly, you can assume that any distribution in that Hilbert space is sort of Gaussian. It's the same idea here. Distribution is not that complicated in hidden layers. Yes.
Sorry, just for my own clarification, the reason we're doing something like batch normalization is because we're doing stochastic gradient descent, which randomly chooses batch of data to go through, and hence the distributions are different at different layers for different batches?
Not necessarily, even if we don't do batch gradient descent. Suppose that you do gradient descent, not batch gradient descent. Still, that could be a problem. Still, you have a hidden layer here, and some nonlinear function which can change the distribution completely. And you don't want this to happen, It's a very nonlinear function, and you have ax plus b, and then this nonlinear function should be applied to this. A small change on ax plus b may push you from this regime to this regime.
But if we see all of the x's together in normal gradient descent, then there won't be a change in different epochs, right? As we're going through training, the distribution will remain the
No,
same.
ax plus b is different. You're talking about the gradient, which is the same. But ax plus b is different, because you change a and you change b, right? So ax plus b is different, and a small change in ax plus b may shift you from this part of the activation function to another part of the activation function, which changes everything. Yes?
Okay, this is just ballparking. Could it be that this model may predict something out of nothing? Like,
What do you
if the
mean?
original data did not have any predictable distribution in the first place.
If, sorry?
If the original data did not have any predictable distribution in the first place, like it's just very rough and it's erratic.
You mean it's noise?
Yeah, it's like very noisy. So could this method like infuse some kind of distribution which is like fabricating some pattern out of nothing?
Well, I don't think so. Fabricating pattern out of nothing could happen in any complicated model. If your input is noise, there is no underlying structure in terms of the distribution. Theoretically, you are not able to learn anything out of this, right? But you have very complicated function. You may be under the wrong impression that you have learned something,
Yeah.
which is not true. This can happen anywhere when you have a complicated function, including neural network. And whether or not batch normalization intensify this or not, I'm not sure. But in any complicated model, this could happen. That you're under the wrong impression that, okay, we learned something here.
Yeah. Like
Yeah.
we don't really know if there's a trend in the data, but then we run this and then we get a trend somehow.
Yeah, have you seen these papers that quite controversial papers that comes once in a while, and someone claimed that I have identified a gene which is correlated to being or not to being or not being religious, or to believing or not believing in God, for example. There's a gene which contributes to this. I was doing gene selection for a project, and I was under the impression that everything works fine. And I was debugging my code, and I realized the labels that I'm fitting to the model is not really the basically labels of patients who has this disease, who doesn't have this. It was gene expression data. Gene expression data, you have many genes and a small number of patients. You have 100 patients, but you have 8,000 genes. So it's 100 points in like 8,000 dimensional space, right? So I realized that what I'm fitting to the model is completely random vector. It has nothing to do with these patients. Still, we are finding a gene, okay? So it's quite clear what's happening. You're in 8,000 dimensional space. You have 100 points there. It's pretty easy to fit, a hyperplane. Take a hyperplane which goes through. It doesn't matter what your labels are, It doesn't matter really what's your label. And take your labels at who believes in God, who doesn't believe in God. You're going to find something. so it is always possible that if it's too complicated, if it's very high dimensional, you have many parameters, in these situations, it's possible that wrongly you think that you have learned something, which is not true, including here. Okay, so I just go quickly through these slides. You know, we covered this before when I showed you this Jupyter example for this digit recognition example that we did in the other day. Here I put the slides. You know, these are the review of what we did in class, just to show you that in any of those steps that we did, there are many other things that you can do. There are many other parameters that you can change. We define model structure here. And when we define model architecture, for example, we use this activation function to be ReLU. There are many other activation functions that you can use. And there's a long list of them. You know, you can just take a look at the slides later, you know, just to get familiar with some parameters that you can change in the examples that I've already provided on the web page. Just to mention that dropout that we learned in Keras is just a layer. So the way that you add a dense layer, say here we had a dense layer of 128 nodes with this activation function. So you can add another layer to the network, basically say model add dropout. And then Keras will do dropout for you. And this 0.2 is the parameter of the Bernoulli function that should apply to the output layer of dropout. So it means this is the portion of the nodes that is going to be non-active. Also, batch normalization is a layer in Keras. So you can just say model add batch normalization. That's it. So for loss function, we use mean square error. This is a long list of other type of loss function that you can use in Keras, and it's built in. And for optimization, we use stochastic gradient descent. Again, this is a list of other type of optimization that you may want to use, and you can try that. So the difference between these methods of basically optimization is that some of them get to the mean faster, some of them slower. You know, these are, say, for example, the red one is stochastic gradient descent, and this blue one is Adam, which is more common these days. So it goes faster to the mean, takes a better path to the mean compared to stochastic gradient descent, for example. Okay, any question? Yes.
So in Keras, you have to do the batch normalization after every layer if you want to do that.
It's up to you. You know, it's up to you. You see the models that they have done this, but intuitively, it seems that you have to do it after any layer. It makes sense to do it after any layer. In practice, you may want to do it after some layers, you know, because it's not quite clear what's going on here. But yeah, I mean, if this intuition about covariate shift is correct, you have to do it after each layer. Okay, so the next topic that we are going to cover in this class is convolutional neural network. Convolutional neural network actually is a neural network which has a convolutional layer. And convolutional layer is a layer consisting of three parts: convolutional stage, detector stage, and pooling stage. So these three together in a layer makes a convolutional layer. And if you have a neural network with at least one convolutional layer, then this network is a convolutional network. Okay. Okay, the first step in a convolutional layer is convolutional stage. Okay, so we are convolving the input with another signal. So I'm sure you are familiar with the concept of convolution. This is the definition of convolution. If you have two signals, you can convolve these two signals, and this is the definition of convolution. And if you remember, convolutional theorem basically says that, it has a close relation with Fourier transform. If you take Fourier transform of the first signal times the Fourier transform of the second signal would be the Fourier transform of the convolution of these two signals. It can be defined on continuous domain. It can be defined on discrete domain. Basically, when you have two signals, it's as if you're flipping one of these signals and you shift it. And then you multiply this to the other signal and then sum it up, from minus infinity to plus infinity. In discrete domain, of course, if you have a limited domain, you're going to compute the summation over that limited domain, not from minus infinity to plus infinity. And it's not just for one-dimensional signal. You can apply it to two-dimensional signals, to three-dimensional signals, and so on. There are two concepts. One, convolution. The other one is cross-correlation. And cross-correlation and convolution are pretty similar to each other. In convolution, you are flipping the second signal, then you shift it and multiply. In cross-correlation, you don't flip it. You just multiply it. In many implementation of convolutional neural network, what has been implemented is, in fact, cross-correlation, not convolution. But in this course, actually, we don't, we will not be picky about this, that this is really convolution or it is cross-correlation. Oh. What was the key again that?
Windows P.
Windows what? P. See, we have two signals, and here actually we are computing cross-correlation, so we are shifting one of these signals, multiply to the other signal, and take the summation. So that would be cross-correlation between these two signals. And if you do convolution, you have to flip the signal and then multiply and take the summation. So that's cross-correlation. And this is convolution. See, this signals has been flipped, and then you multiply them. So cross-correlation actually shows the similarity between two signals. So if this is high here, means at this point, these two signals are similar. At this shift, at this time shift, these two signals are similar to each other. And if it's a small, means at this time shift, they are very dissimilar. Okay? So that could be helpful. The fact that we can use cross-correlation to find similarity could be quite useful. Let me show you. Okay, see, I have two signals here, this signal and this signal, and I compute cross correlation between them. So it's discrete function. So this value of the function times this one, plus this one times this one, plus this one times this one. So at this time shift, at time 0, that's the value, 7 point something. Then suppose that I shift it, and then compute again this quantity. And I just keep going, you know. See, at this point, at this shift, look at this value, 19.41. It's a large value compared to 7. At this time shift, these two signals are similar. See, similarity between these two. Then here, they are very dissimilar. It's a negative number. And I can do it again. Again here, you know, 17 is a relatively large number because, you know, you can see the basically similarity again here between these two signals. See this one with this one, this with this, you know. So basically it can show, I mean, it can tell me at which time shift these two signals are similar to each other. The value of cross correlation can show. So now suppose that you have a two-dimensional signal like an image, and you are computing the cross correlation of this image with another image. So basically, it show. I mean, the values of this cross correlation should tell me the points that these two images are very similar to each other, right? So this could have many applications and could be very useful, including okay, that's the original image. That's the original signal that I have. And this is the second signal that I want to convolve with this, or I want to compute the cross correlation. The second one is similar to edge. Look at just the contrast. You know, it's a simple 3 by 3 matrix. But this 3 by 3 matrix actually look like because what is edge? Edge is basically, you know, a line that you have a contrast on both sides of the that line. You know, the color will change significantly. So we go from black to white here. So it's similar to edge. So I convolve this, or I compute cross correlation of this and the original image. And this is the result of this cross correlation. You know, just remember what we had in the one-dimensional cross correlation. So the higher values corresponding to the positions that we had similarity. So higher values have been highlighted here and are positions that they are similarity. Similarity between this one and this one means similarity between edge and the image. So this is basically an edge detector. You know, we can compute the edges of this image. If I change it to this one, I will get this one. I don't know how clear is this. You know, in one case, actually, These are sort of horizontal edge. In the other one, it's like vertical edge. Maybe I show you an example which is more clear than this. So this is the original image, and this is the second signal that I convolve with this one. If I convolve this one with this, I will get this. It just detects horizontal edge. If I do the cross correlation between this one and the original image, I will get this one, which capture only vertical edges, right? And this is basically the combination of both of these two, which gives me all of the edges of the image. Okay. So in the literature of convolutional neural network, we always convolving a signal with the input signal, and we call this signal that is going to be convolved with the original one a kernel or a filter. Okay. So the first stage of convolutional layer is convolutional stage. In convolutional stage, we have a kernel. A kernel looks like this. And it's going to be convolved. We're going to compute the cross correlation between this and the original image. Okay? And it's going to have an output. This output is look like this, which is called feature map. Okay? So we convolve a kernel or a filter to the input image, and the output is called feature map. So that's the first step in convolutional net. And you can see here that through this convolutional stage, we may learn something useful. We may learn a feature map, which basically are the edges, for example, of the input image. Could be, depends on this kernel, it could be another feature which is useful. Okay. In convolutional neural network, we don't fix these kernels. We let the model to learn this kernels. So intuitively think about this way. You are doing a classification problem. The output is y, and I want to predict y. Along the way, there are some kernels that are going to be convolved with the input and produce some features. So ahead of time, I don't know which feature is useful to predict y. I let the network to decide which kernel is useful. Useful means that it produces features which are discriminative enough for this classification problem, and led me to predict y precisely or in a better way. Okay? So that's basically the idea.
Sorry, so you do have to pick the kernels in advance, right?
No.
Oh, okay.
No, you're going to learn them. It's like weights in neural network. Soon we are going to see that they are exactly weights in neural network. Yes?
In the image that you showed, the feature map image, for example, the image of the outline of the elephant that you get right over the elephant, that is obtained after sliding the first convolutional window over the entire image, right?
Mm-hmm.
And next to that were there were two other images, bottom right side, right?
Yeah.
What are those? How do you get them both? I believe one is pertaining to the vertical edge window and the other one's horizontal. But how do you get that from the?
You just add them on. You produce the first image, you produce the second image, add them. Because in the first image, any horizontal edge is large value. Everything else is very small. And the other one, like horizontals are large, and these one are small. So add them up. Any other question? Yes?
So the signal in that example is just the grayscale number corresponding to the image?
Yes. Yes. It's a 3 by 3 matrix, which was basically 1, 1, 1, 0, 0, 0, negative 1, negative 1, negative 1.
And similarly, the elephant image is also divided into a 3 by 3 matrix to get the.
No, it works like this. You know, this is the original image. And then you have a kernel. You know, this is a kernel, like 3 by 3 kernel. And this kernel, in this case, is 1, 0, 1, 0, 1, 0, 1, 0, 1. You multiply this kernel to this portion of the image, element-wise, and you add them up. You know, this is like cross-correlation. Yeah. 1 times 1, 1 times 1, so 2, 3, 4. So you're going to have 4 here. Okay? That's, I'm producing the feature map here. Then I shift this kernel 1 step, 1 pixel, and do exactly the same thing. So I have 1, 1, 1, so it's 3, right?
The output signal will not have the same dimension as the input image, right?
Not necessary, no. No. And then, you know, you keep just going. And you produce this. No, it doesn't have the same size as the original one. You can have the same size as the original one, but you need padding. Padding means that you're going to expand this image. You're going to have add some columns and rows to this image. And when you are here, excuse me. You may assume that there are 2 more columns here, 2 more rows here. And padding could be like 0 padding. You may add just zeros here. Or same padding means you just replicate these columns and rows. But in general, it doesn't need to be the same size. Yes?
Yeah, so the horizontal edge one would pick up the horizontal features, and the vertical edged filter would pick up the vertical filters, right?
Right.
So if you want to build a CNN that you want to, like, let's say face detection, for example, the distribution between faces, where most of the features are circular. So how would you design? Would you have a filter which has like circular?
You know, we don't decide about the kernel ahead of time in convolutional neural network. That was just an example to show you the effect of a kernel on an image. In convolutional neural network, you don't set the values of the kernel. These are parameters of the model which will be learned through backpropagation. You know, this is the kernel that's supposed to be convolved with the input image. And I don't know what the values are. These are my parameters. I'm going to just set some initial value to this and do backpropagation. Through backpropagation, the algorithm decides about the value of this kernel. But decides based on my cost function. My cost function is to predict the y correctly. If it's face detection and if your features are circular, it's have to produce features that is useful for face detection. But we let the model to decide about it. We don't decide. We don't set a kernel ahead of time.
If you want to set the initial parameters of your kernel, wouldn't you choose a circular distribution for the kernel? That way, wouldn't it learn faster because the circular edges would coincide quicker? You guess the cost function would converge quicker as well?
No, that's not a common practice because usually, you know, there are a couple of kernels that people forgot the name of the kernel that I want to mention. But there are a couple of kernels that people observed practically that could be helpful kernels, you know. But in general, you know, something interesting about machine learning is that you let the model to decide about the features. Sometimes the features, you know, I don't have the exact, I can show you this example later, that there's a set of pictures and you want to classify between frontal view and side view. Okay, so if you ask a person to find a feature to make distinction between these two, You can think of any feature except the feature that the model learned. Feature that the model learned is just light here at the this edge of the nose, because when it is like sided view, it's very bright. When it's frontal view, it's not. You never think that this is an important feature here, So we let the model to learn what feature is important instead of deciding for the model that. But there are some structures that have been observed that could produce useful features as initial value. Sometimes we see that kernels are assigned randomly instead of being learned. In that case, some structure could be useful again.
I think though that people do use transfer learning, so they'll use the lower layers of a network that was pre-trained on ImageNet if they're doing a sort of related task. But they find that speeds up the training, so it has useful features, but they didn't handcraft them.
Yeah, but that's different, the problem of transfer learning is not exactly the same, but it's similar to the problem of domain adaptation that I explained to you. You learn a model for a task, but you want to transfer this model for another task. So I learned, for example, image or pattern recognition or image recognition, and ImageNet, for example, which has objects in it like pen and airplane and car and different things. Okay, but I want to apply it to medical imaging problem. We never observed such images in ImageNet. Okay, but the idea of transfer learning is that maybe the knowledge that we already learned here is useful here, because all images are made of some primitive shapes. All images are made of some corners and some vertical and horizontal and angles and so on. So maybe the features that I learned here for ImageNet are useful in classification of this image as well. So one technique of transformation learning is to use a pre-trained model. Say you trained AlexNet on ImageNet. You use this pre-trained model for this new one, and you just add some layers to it, and you just learn the new layers, or you fine-tune the weights that you have learned before. This is different from actually what we're discussing here. Those features have been learned, and sometimes what I'm saying is that you can't decide ahead of time that what is the kernel, what is the weight. Okay. So that was cross-correlation or convolution, whatever. If you think about this, think about what's happening here, you can actually see that by the whole story of convolution and cross-correlation and convolving a kernel to the method, what we are doing is two things. One is making the weights. Just think about feed-forward neural network. Suppose that you have feed-forward neural network, and you are making the weights of this feed-forward neural network sparse. In feed-forward neural network, I have this input layer, and I have this hidden layer. So there is a matrix as matrix of weights, which are going to be multiplied to this input and produce this one. So in fact, there's a weight here which will be multiplied to this value. And a weight here which is going to be multiplied to this value. But this is dense, From anywhere to anywhere, I have a weight. So think about convolution or cross-correlation, that we multiply a kernel to the image, to the input image. If the kernel has the same size of the input image, it's as if for any pixel, there is a corresponding weight that I multiply that weight to this pixel and then add them up, okay? So if the kernel has the same size as this input, it means that, this is one entry of that kernel. This is another entry of this kernel. This is another entry of this kernel. This is another entry of that kernel. So I multiply some weights to each entry of this image and then add them up and produce one element of my feature map, right? But another feature map actually would be another set of weights, which produce another element of my feature map, and so on. But if the size of the kernel is smaller than the size of image, which is the case in convolutional neural network, we had like 3 by 3, for example, kernel here. So it means that I'm not using all of these weights. So the size of kernel is smaller. I'm just using a kernel of size 2, so I multiply the weights of this 2 kernel to this pixel, to these 2 pixels, and I produce something here, right? Then I shift the kernel and do this exactly the same. When I shift the kernel, means I'm 1 pixel down. I multiply the values to these 2 and produce this second element of the feature. And then I shift again. So, but this weight would be exactly the same as this one and exactly the same as this one. And this weight would be exactly the same as this one and exactly the same as this one. So 2 things happen. One is that we make this matrix sparse. Second is that we tie weights. We don't have many parameters anymore. So the parameter here would be exactly the same as this parameter. The parameter here would be exactly the same as this parameter. So in feed-forward neural network, in a dense layer, this value is different from this one. This value is different from this one. And we had all weights. We had weights all over the place, everywhere. But we have done 2 things. Make the weights sparse. Second, tie the weights. Okay? And you remember that we talked about sparsity the other day, that sparsity really is a helpful thing everywhere, including here. One of the reasons for success could be, having a more sparse one. Okay, so in feed-forward, if you have a layer of m nodes going to a layer of n nodes, you have m by n weights. But here you have a kernel of size k. So the order of weights is k by n instead of m by n. So the number of weights are smaller. The number of weights are small. Okay. And we are doing parameter sharing, as I said. This is the same as this one, the same as this one. You tie parameter to each other. Okay. Yes. Size of the kernel? No, you decide size of the kernel. The same that you decide about the size of the hidden layer here, for example. You just decide that this layer should be 32 or 64, 128, whatever. You decide that I'm going to use kernel of size 3 by 3 or 5 by 5 or 10 by 10. There's no good way to design it, actually, at the moment. Yes?
How kernels are stored in memory? Separately from the network?
It is, just think about this as a feed-forward neural network that has less number of weights and have some structures in the weights. In feed-forward neural network, from this layer to this layer, you have a matrix. Now, this matrix, 1 is sparse. Second, have some sort of a structure that a part of the matrix is the same of another part.
So each layer will apply only one kernel?
Sorry?
At each layer, when we go from one layer to another, do we apply only one kernel?
No. We apply many kernels. Actually, it's a good point, but I was about to show it to you practical examples later on. You know, from one layer to another layer, we apply many kernels, not one kernel. Not only one kernel. You know, say the input image, you have an input image. And you apply a kernel to this, okay? And then you shift this kernel and shift this kernel. So it produces a feature map for you. That's not the only kernel that you apply. You apply another kernel also. And it produces another feature map. So there will be another feature map here. And then you apply another kernel. There will be another feature map, you know. So you produces many feature maps. Say you have 10 feature maps here in the first layer. When you want to go to the next layer, if it's a convolutional layer, again you are going to convolve this with a kernel. But here your kernel is not just 3 by 3, it's 3 by 3 by 10. It's a kernel of this form, you know, which is going to be convolved with all of these feature maps and produce another feature. But again, here you may apply, and you're going to apply more than one kernel. So you apply many kernels to this. Okay? Yes?
In the case we had a lot of kernels, the topic of sharing weights would be less effective. Yeah?
No, it's still for each kernel you're sharing weights. You know, think of each kernel. Each kernel is a matrix multiplication, which is sparse and have some sort of a structure. But you multiply many of these matrices. But in each matrix, you have the concept of parameter sharing, and you have the concept of sparsity. Okay. So this is the definition of equivalence. You know, if you have two functions f and g, and if f g of x is equal to g f of x, then by definition, function f of x is equivalent to function g. And this is an example, you know. Suppose that g is an identity function which takes x and produces x, and f is a function which maps x to y. So if I first apply g and then apply f, the output would be y. But it would be the same that if I apply f first and then apply g, because g is identity. So in this case, f of g is g of f. Okay? So in convolutional network, or in general in convolution, actually translation and convolution have this property. So if you translate first and then convolve, would be the same as you convolve and then translate. Okay? You know, if, say, this is an image. This is one signal. And this is another one. You know, this is just a step function, Dirac step function. If I convolve this one with this one, I get this one back as the result of convolution. Okay? But if this is my function, the second signal, and if I convolve this one with this one, then I will get this as the result. Okay? So the second one will appear here, actually. Actually, it's a bad example because I'm convolving a two-dimensional signal with one-dimensional signal. So this is my signal. If I convolve it with this one, it's as if, you know, I put it here, so I get this one back. If I convolve it with both of them, then I will get an image like this. So it will be repeated. So if just think about it this way, this is the result of convolution. But if I don't have this one and I have only this one, that would be the result of convolution. Shift and convolve would be convolve and shift. It makes no difference. So in two-dimensional space, for example, if this is one image and this is another signal that has high values here, like a spark function and 0 everywhere else, and if you convolve them, you will get an image like this. That's the reason that it can be used as edge detection, because it produces a feature map, because you have this feature and you convolve it, and this edge on the image of elephant has been shifted all over the place. When you convolve this, as if you convolve and then shift it all over the place, you get a map similar to those edges in the original image. So that's basically this property is called equivariant, and it's with respect to translation it's equivariant, but it's not with respect to other transformation like rotation or scaling and so on. But in terms of translation, it is equivariant. Yeah, as I said, that's something which help you to learn a feature map, which is useful. Okay, so that was the first step of convolutional neural network, convolutional stage. The second step of a convolutional neural network is detection. Detection is basically similar to activation function that we had in feed-forward neural network. So in feed-forward neural network, we had this layer, and we had another layer here. But we had a nonlinearity at each neuron, right? So this linear sum, a nonlinearity will be applied to this linear sum, which we call the activation function. It could be sigma, it could be ReLU, and so on. So detection or detector stage is this. It's just a nonlinearity function, which is going to be applied to the output of your feature map. So these are your elements of your feature maps, right? With a sparse matrix with some structure. You're going to apply a nonlinearity to it. It's called detection or detector stage, similar to nonlinearity. Nothing new here, actually. And the third step, which is new, is pooling stage. Okay, you have a feature map now. As the output of convolution, you have a feature map. And you apply some nonlinearity to this. Still, you have a matrix of this form. Now, pooling means that you are going to report some sort of summary statistics of this data instead of the raw data itself. For example, I'm going to take the average of these 4 pixels. So this is 2, this is 3, this is 1, this is 0. Okay. This is 2, this is 3, this is 2, this is 1. And here, in a stat, I'm going to report 2 plus 3, 5, 7, 8, divided by 4, 2. So I'm going to report 2, 2, 2, 2. So I'm going to summarize this. Take the mean of them, for example. take the max of them, for example. Instead of taking the mean, taking the average, I may take the max. So the max here is 3. Okay. This is called pooling. I may do pooling with downsampling. So instead of reporting 3, 3, 3, 3, I may make the size of this feature map smaller and report only 3. Okay, this is called pooling. So pooling is basically could be different form. You can take the average of rectangular neighbors, like our first example. You can take the L2 norm. You can take the weighted average. There are many different types of pooling. The popular one is max pooling. Usually people take the max of these. So you can think of this as sort of summary statistics about the data. You know, this is, say, for example, the output of detector stage. And this is the pooling stage. The pooling stage could be the same. I mean, the output of pooling stage could be the same size of the feature map. In this case, actually, we are looking at, you know, this the 3 and take the maximum. So I had another one here, and this 3, the maximum was 1. And then this 3, the maximum is 1. And then this 3, the maximum is 1. And then this 3, the maximum is 0.2. And if it's with downsampling, like this one, you reduce the size of this feature map. And the size of the output, the size after the pooling is smaller than the size of the feature map. And you may have different stride, means that when you do pooling, you may do pooling here and then do it here. Or you may shift a couple of pixels ahead and with a stride 2 or 3, you know, take a step of 2 or 3 and then do the pooling. Okay, I'm going to explain the effect of this pooling in the next lecture, but I encourage you to look at a video that I posted on Piazza. It's a talk by Jeffrey Hinton, and the title of the talk is "What's Wrong with Convolutional Neural Network?" Basically, he believes that pooling is a very bad idea, and it works, but it's a bad idea, and you shouldn't have this. It's a very high-level talk. It's not mathematical, but it's a very high-level talk and led you to think about intuition behind neural network modeling brain and how convolutional neural network, not mathematically, but intuitively, how does this relate to the brain? And from this perspective, why it works and why we shouldn't have the pooling there, because he believes that, you know, it's completely different from what we are doing in our brain. It's an interesting talk, and you know, lets you to think more in depth about the intuition and insight behind these models. Yes.
Can we interpret this pooling as a form of regularization? Because we're not exactly, we're actually just not overfitting limits. We're actually just trying to generalize certain.
Yeah, you can, because I mean, one possibility actually is if this pooling is severe, you know, you may even underfit the model. You know, that's something that in practice you may observe. So yes, you can think of this as sort of regularization. But it has other properties. I mean, those who believe in pooling, actually, they shows many good properties for pooling, which is not just a regularizer. You know, it can fix, you know, the problem of having varying length It can make your model basically invariant with respect to translation, which you're going to see later. They believe it has many good properties, but Hinton believes that no. I mean, some people, some researchers, yes.
By pooling, aren't we losing like valuable information by reducing the feature map?
Sorry?
We're losing valuable information by reducing the feature
Yes.
map.
Yeah, you're going to lose some information, definitely. It's summary statistics. It's not everything that you have.
So I guess it's for computational benefit. Or
Computationally, it's beneficial. I think that was the first motivation for computation, that, you know, it's too large to go to the next layer. Let's make it a small. How should I make it a small? Take average of each, you know, rectangle. I think that was the first motivation. And then second, you know, I mean, after that, secondary, they have observed that, yeah, it makes resistance with respect to translation, you know, of the image and so on. But that was the first motivation, that computationally it's going to help, that it doesn't lead to feature maps to explode, you know, make it smaller by taking a summary of that.
But that can also be learned, pooling.
What do you mean learned? I mean, the parameter?
Yeah, parameters of pooling. Can be
Yeah, I mentioned there is a paper, I think 2012, that they are trying to learn the operator of pooling. There's another paper they're trying to learn the region of the pooling. Instead of a rectangle, do sort of clustering and turn the area that you have to do pooling on. Yeah, there are these variations. But vanilla common convolutional neural network is that you just take a rectangle and usually take the max of that. Max pooling is most common one. Okay, don't forget to get your SharkNet account. You know, I repeat this every day, and download ImageNet and see how large it is and how much computation you need. You know, don't wait until the last day. Okay, see you next week.